In constructing a molecular orbital diagram for a diatomic molecule, we have seen that the pi molecular orbitals, the bonding and anti-bonding pi orbitals, tend to be degenerate. That is to say, the px and py orbitals both create molecular orbitals that are the same energy as one another. And want to explore this a little bit in light of how we populate those molecular orbitals with electrons. All right, so for example, what I'm going to do is show what all of the possible combinations are, say, for a set of pi bonding orbitals. And the way I'm going to do this is I'm going to, for example, draw the two degenerate orbitals and then give them indices that indicate their lambda quantum number. Now, you may recall that lambda, if we were to draw the axis on which the internuclear bond occurs, and this is the z-axis, that we have an azimuthal angle phi that goes on there, and lambda essentially was the number of nodes that we would encounter, or number of nodal planes that would break up that azimuthal angle. So for example, if there was one nodal plane, then lambda would be equal to 1. Now, at that time, I was describing that lambda could be 0, plus or minus 1, plus or minus 2. I want to change that definition a little bit and reserve lambda for the absolute value of the number of nodal planes that might occur across that coordinate, and use another designation, we'll call it m sub lambda, that will be lambda with sign. So m sub lambda, when lambda is equal to 1, would be plus or minus 1. But notice that it does not equal 0, as it does, for example, in the atomic orbital case. M sub lambda 0 would correspond to the p orbital that lies along the z-axis, and that actually forms a sigma bond, not a pi bond. So this is the one that's going to be more relevant for the pi bond. So that's why I've labeled these two slots over here, plus 1 and minus 1. Now, there are several different ways that we can place two electrons in these orbitals. So I'm going to draw these out diagrammatically. There's actually 6 different ways we can do this. And each of them has corresponding m sub lambda values of plus 1 and minus 1. All right, so if we were to draw electrons in here, these might look something like this. For example, I could have both of the electrons spin paired in one of the two pi orbitals. I could have them split between the two orbitals and still spin paired, or spin paired in this way. I could have them split between the two orbitals and not spin paired, which could correspond to those two. Or I could have them spin paired in the other one of the pi orbitals. So these are the 6 different ways we could do that. Now you may be thinking to yourself, or maybe not, that there should be 8 different ways, because I have 2 possible spins and I've got 2 different directions, for orbitals here. But the other orbitals that we might consider would be to have both of them in one orbital but not spin paired. But we can't do that because that would violate the Pauli principle. So how would we decide among these various possibilities which ones would be the most suitable when we're filling up the electrons in a bunch of molecular orbitals? Well, it turns out that Hund's rule that we looked at in the case of atomic orbitals has some implications for molecular orbitals as well. And it says that states with higher multiplicity, so higher spin multiplicity, are going to be the ones that are preferred. Okay, so this was I think the first of Hund's rules that dictated which of the terms for atomic symbols, atomic term symbols, would be the one with lowest energy. And so the same thing holds true, which means that we're going to prefer these middle 4 pairings of electrons in these a little bit more than we're going to prefer the N2, where we put both electrons in the same of the pi molecular orbitals. Now, why would this be so? Why is there an intuitive reason why we might expect this? Well, if you think about it, when we have electrons sitting in the same spatial orbital, that in some sense increases the electron-electron repulsive forces. So when they are in same orbital, we have more intense electron-electron repulsion. So that's why those states, the ones on the two ends, tend to be preferred less so than the ones in the middle, where we can put one electron in each orbital. All right, now why is this important? Why do we care about this stuff? Well, it turns out that the pairing of electrons does a lot to provide a molecule with certain magnetic properties. And there are two particular outcomes that we want to pay attention to. One is called a paramagnetic molecule, and the other is a diamagnetic particle, and I'm writing them in opposite order. So diamagnetic, what does this mean? When a molecule is diamagnetic, it means that it is not attracted to a magnetic field. So maybe it's a way of saying that it's not very magnetic. However, if it's paramagnetic, and that's magnetic, poorly written, then it is attracted to a magnetic field. All right, so what does this have to do with Hund's rule and the electrons? Well, in the first case, this means that all electrons are spin paired, which is to say cases like this one up here, where you have two electrons spin paired. That would, if that were if everything else was full, then this would be the case. It would be a diamagnetic molecule. Obviously, the opposite is going to be true for paramagnetic. It says that there are some electrons that are not spin paired. So in other words, these cases, like this, would be a case where we might have a paramagnetic molecule if that's how those orbitals were filled. All right, so what would be a good example of this? Well, the one that's quoted most often in books and that you'll see in some of your lesson plans is the case of oxygen. So let's draw out what its molecular orbital diagram should look like. Now I'll remind you that oxygen has, atomic oxygen has a electronic configuration of 2s2, 2p4. Now I'm going to ignore the 1s2s because that forms a core set of electrons, so they're not going to participate in the bonding at all. Those are just going to be core electrons on the oxygen atoms. But we'll have a set of 2p orbitals, so let's draw those up here, and 2s orbital, we'll draw that down here, and each oxygen will have equivalent sets of atomic orbitals. So here are the 2s, here are the 2p. All right, we know that the 2s will combine to form a sigma G bonding orbital and a sigma U antibonding orbital. And this, in fact, is 2 sigma G and 2 sigma U because the ones were used up in our core electrons. All right, for the p orbitals, the lowest one is going to be a sigma G. Then we'll have 2 pi U orbitals. These are basically the pi bonding orbitals. Then we'll have 2 pi antibonding orbitals and a sigma antibonding orbital. So this is sigma U, and these are pi G. All right, so now when we fill in our electrons, I'll try to use a different color for this. Clearly we're going to have 2 electrons, so 2 electrons in each of the 2s orbitals, so that means a total of 4 in these. So all of these are filled up. There's not going to be any net bonding advantage to having electrons in these orbitals. For the 2p's, I'm going to have a total of 4 electrons. So we'll have this set up for the atomic oxygen, and I should draw the little lines connecting these to the molecular orbitals that they produce. All right, so when I start filling in the bottom, I've got a total of 8 electrons. So I'll have 2 down here, I'll have 4 more here, and I'll still be left with 2 that have not been assigned. So they will come up here. Now this is the whole point of this exercise that we did up at the top. We know now that because of Hund's rule, these 2 electrons will not be spin paired in the same orbital. So as a result, what happens is that these two unpaired electrons are the things that cause oxygen to be paramagnetic. Now I want to say a few words about this molecular orbital diagram, and I hope it's large enough for you to be able to make it out here. All right, first of all, these things down here do not really participate in the bonding. So in fact, what we have here are non-bonding orbitals. Okay, they are in the valence shell. It's probable that these 2s orbitals are mixing some with the 2p's to form the molecular orbitals for bonding, but it's not a strong amount of mixing. So these are, we can essentially treat these almost the same as though they were core electrons. So all of our bonding action is taking place up here in the 2p orbitals. The three bonding orbitals down here at the bottom is where we get most of the bonding strength for oxygen. Orbitals. And the two up here are anti-bonding orbitals. All right, so we could actually write a molecular orbital conformation configuration for oxygen that would look something like this. And I'm going to include the core electrons in this also. So we would have 1 sigma G, which has 2 electrons in it, 1 sigma U, which are the anti-bonding components of the 1 sigma G. Then we'll have 2 sigma G and 2 sigma U. And these both have 2 electrons in them. These are the 2 orbitals that are drawn here and here in the molecular orbital diagram. I'll have 3 sigma G, which has 2 electrons. I'll have 1 pi U, which are the bonding pi orbitals, and these have 4 electrons in them. And then finally we'll have 1 pi G with 2 electrons. Now, when I write this, it kind of obscures the fact that these 2 electrons are not in the same orbital. So another way we might write this, if I write 1 pi G2, is that it's kind of like 1 pi G minus 1 with 1 electron in it, and 1 pi G plus 1 with 1 electron in it. So this would basically tell us for sure that these 2 electrons are not spin paired in the case of the oxygen molecule. They're separated and cause the molecule to be paramagnetic. All right, so this gives you a little bit of an exercise in how to construct these diagrams. I should note that the bond order for oxygen, we always think of oxygen with a double bond. It does indeed have a double bond, but the bond order comes about because it's got 6 electrons in bonding orbitals and 2 electrons in anti-bonding orbitals. So that's why we get 2 bonds in oxygen, not because it just makes 2 bonds, but because some of its electrons are actually in anti-bonding orbitals. I hope that you'll be able to use Hund's rule to construct valid molecular orbital diagrams, use those to determine the bond order, and also to assess the magnetic properties of different molecules. And it could also be for ions as well. So for example, if we had formed an O2 2+ ion, which is a rare beast, but this in fact would be a diamagnetic species, because we would have removed the 2 electrons that are in those 2 pi antibonding orbitals.